This is practice test 3. We're looking at the first question, part A. A copper block is removed from a 300-degree oven, which I've drawn here, and we drop it into 1 litre of water at 20 degrees Celsius, which I've drawn here. Then the water quickly reaches 25.5 degrees Celsius and then it remains at that temperature, and we can assume that none of the water is converted to steam. Part I is asking us, what is the final temperature of the copper block? Explain. So what we were told in the question is that the water quickly reaches 25.5 degrees Celsius and then it remains at that temperature. It's asking us, what is the final temperature of the copper block? Now, what we know is that the temperature is not changing. It's not changing anymore. If the temperature is not changing, that means that the system is in thermal equilibrium. And therefore, if the system is in thermal equilibrium, both the copper block and the water must be at the same temperature, because at thermal equilibrium, there is no energy transfer between objects in the system. So we can say that the final temperature of the copper block is 25.5 degrees Celsius as well. Now for this question, if you identified that the system is in thermal equilibrium and the temperature is not changing anymore, you get a mark for that. And then if you correctly identified that the final temperature of the copper must be 25.5 degrees Celsius, you get a mark for that too. Therefore, the number of marks for part I is 2. Now for part II, the question is asking us how much heat does the copper block transfer to the water. So if this is our copper block, we're transferring heat to the water. We give heat the symbol Q, and that's what we're trying to work out. Now, we know that the system's in thermal equilibrium, and we can say that we assume no loss of heat to the surroundings. If there's no loss of heat to the surroundings, that must mean that all of the energy that all of the heat that was transferred away from the copper must have been gained by the water. And when I say heat lost and heat gained, this is more the energy that transferred away from the copper was transferred and gained, it was transferred to and gained by the water. Now this is what we're looking for. Now this heat, as we explained just before, heat is given by the symbol Q, and the equation for heat transfer for two objects that are at different temperatures is M times C times delta T, M being the mass, C being the specific heat, and delta T being the change in temperature. So we don't need to know anything about the copper yet, we just know that the heat gained by the H2O was the heat lost by the copper. So let's do this for the H2O. Now we know some things about the H2O. We know what the initial temperature is and what the final temperature is. Therefore, we know what the change in temperature is. It's going to be 25.5 minus 20.0, which is 5.5 degrees Celsius. Does this matter if this is in degrees Celsius or Kelvin? No, it doesn't, because it's a difference in temperature. And I'll just show you really quickly why that's the case. If I was to convert both of these to Kelvin, both the 25 and the 20 degrees Celsius, you're adding 273.15 to both, and since it's a difference, they just cancel anyway. So we have 5.5 degrees Celsius. From your formula sheet, And from the table that was given in the question, we know what the specific heat of water is. It's 4186 joules per kilogram per Kelvin. All we need to know now is what's the mass of the water. Well, what were we told with the water? We weren't told the mass, but we were told something. We were told the volume. How do we relate volume and mass? Well, that's through our density equation, where density is mass divided by volume. Therefore, mass is density multiplied by volume. Density of water, also given in the table in the question and on your formula sheet. It at 15 degrees Celsius, it's 1,000 kilograms per meter cubed. Now we need to multiply that by a volume that is also in meters cubed. Now, if you know your conversions between volume and cubic meters, that would be useful. A useful one to remember is 1,000 liters equals 1 cubic meter. Therefore, 1 liter, which is what we have, is 1/1000th cubic meter. So if we multiply this by 1/1000th cubic meter, we get the mass of water is 1 kilogram. So let's sub all that in. Degrees Celsius or Kelvin. So our temperatures cancel, our masses cancel, and we are left with a value in joules, which is 23023 joules roughly. But this is far too many significant figures. All of the information we've been given, the least number of significant figures in the question is 3. So let's change this to 3 and we'll make it kilojoules. For this question, if you were to correctly identify that the heat lost by the copper is the heat gained by the water, you would get 2 marks for that. And then if you subbed everything in correctly and got the correct value, you would also get 2 marks for that. Therefore, part II is worth 4 marks. So part III is asking us what is the mass of the copper block. So we know the heat lost by the copper equals the heat gained by the water. And we know what our equation for heat is. It's mc delta T. So let's sub in what we know. We know this is going to be mc delta T, and this is going to be the heat gained by the H2O, which is 23.0 kilojoules. Now, if we're talking about in terms of heat lost by the copper or heat gained by the H2O, since it's actually the heat that's being lost by the copper, we can actually put a negative on this. And this actually makes more sense in a little bit. So this is the value that we want here. So let's rearrange this equation for that. So we know what the specific heat of our copper is. It's given to us in the table in the question. So it is 390 joules per kilogram per Kelvin. We also know what the change in temperature is. It's starting out at 300 degrees Celsius and going down to 25.5 degrees Celsius. You can see here that this delta T is actually going to be a negative, which is why it makes sense to put a negative here. So let's sub in everything we know. And then when you calculate that, you get 0.215 kilograms. For this question, if you were to get to this line here, that is 1 mark. If you were to sub in all the correct values, that's another mark. And then if you get the correct answer, that's 2 marks. So part III is worth 4 marks. Okay, part 4. Part 4 is a bit more complicated. Part 4 is telling us that 3 grams of the water that we originally had in our 1 litres has now being converted to steam, but everything else remains the same. Now we want to know what the final temperature of the system is. So the easiest way to actually look at this question is to consider that we have three different entities. We have the copper block that's originally at 300 degrees Celsius. We have the H2O, which is in total 1 litre. However, we also have a component of that H2O, which is steam, 3 grams of it, which goes from 20 degrees all the way up to 100 degrees and is converted into steam. So really, the mass of our H2O is no longer going to be 1.00 kilograms. It's now going to be 3 grams less. Therefore, the mass is actually 0.997 kilograms. And that's because 3 grams of that original H2O is being converted into steam. So now we need to know what the final temperature of the system is. We know what the final temperature of the steam part is because we need to transfer enough energy to that 3 grams of water such that it gets up to 100 degrees and then enough to convert it from water into steam. And we know that you actually need to input extra energy in to make that phase change. So that's what we're about to write down here. So if we know that there's no energy being transferred between this system and the surroundings, that if we were to add up the heat transferred to and from all of these objects, they would end up being 0. So we say Q of the copper, or the heat transferred from the copper, goes into the original H2O to change its temperature, plus it goes into the steam component, plus it goes into converting the water from 100 degrees into steam at 100 degrees. So I'll say water to steam. Okay, so now what we can do is we can write everything down. So for normal processes where we don't have a phase change, this is easy. However, this last component is actually converting the water to steam. Now remember, we don't actually have a change in temperature here. It's still going to be at 100 degrees, but we are going to be utilizing the latent heat of vaporization. So we have 3 grams of water, which will be this delta M, multiplied by the latent heat of vaporization. This delta M, it's a delta because it's the change in mass of the object when it's going to the higher state. So in this state, it would be the change in mass of steam. Now we're assuming that all of this 3 grams is converted into steam, therefore this delta M is going to be 3 grams. So what we actually want, we need to keep expanding on this a little bit. So here, what we actually want is we want this TF. We want the final temperature of the water and the copper block. Remembering that we already know the final temperature of the water that's going to become steam. So we basically need to rearrange this equation such that TF is on its own. So I'm going to do that really quickly now. Okay, so now we're at that point. I'll just erase everything above here to give us some space. And now what we can do is we can sub everything into this equation. And then when you do all of that, you get 23.69 degrees Celsius or 23.7 degrees Celsius to 3 significant figures. Now marking for this question, if you got the original equation, where before we started rearranging it, you got a mark for that. If you got all the signs correct, you got a mark for that. If you then rearranged everything and you got to the correct answer, you got 2 marks for that. Also, if you remembered to include the component for steam, you got a mark for that. So therefore, part 4 is worth 5 marks. Therefore, this whole question is worth 15 marks. Okay, so part B is a PV or a pressure volume diagram question. So here we have a cyclic process going from A to B to C back to A. And we've been told in the question that the process A to B is isovolumetric, which means that the volume doesn't change, and 303 kilojoules of heat enters the system. The process B to C is isothermal, which means that the temperature doesn't change, and 333 kilojoules of heat enters the system. And process C to A is isobaric, which means it occurs at constant pressure. While showing all of our reasoning, we need to calculate. In part I, the change in internal energy of the system as it goes from A to B. So we're asked about the change in internal energy. I will write this down as our equation. So we know that for the change in internal energy, the formula is Q plus W, where Q is heat and W is work. Both have the units of joules. So the heat for the process from A to B, we have been given. It was 303 kilojoules. We just need to now work out what the work is. Now we have an equation for work. It is negative the integral of pressure times the change in volume. Now the really important thing to remember about work is that work is non-zero when there is a change in volume. If there is no change in volume, that means that work is 0. Now here, we were told that A to B is an isovolumetric process, which means that there is no change in volume. Therefore, the work for the process A to B is 0. Therefore, the internal energy is just the value for heat, which is 303 kilojoules. So for part I, if you recognized that the change, that the work is 0 because it is isovolumetric, you get a point for that. If you correctly give us the formula, there's a point for that. And then if you get the right value, there's a point for that. So part I, there are 3 points available. Part 2I is asking us about the work done on the system as it goes from B to C. So we are asked about the work. We were told in the question that the process from B to C is isothermal. If it is isothermal, what does that mean for our change in internal energy? That means it is 0. We were also told that 333 kilojoules of heat enters the system during the process. That means that Q is 333. Therefore, the work done on the system as it goes from B to C is negative 333 kilojoules. For this question, if you correctly identified that the change in internal energy will be 0 because the process is isothermal, you get a mark for that. If you got the negative sign here, there's a mark for that. And if you got the correct value, there's a mark for that. So part 2I, you get 3 marks. Part 3I is asking us about the heat entering the system as it goes from C to A. So what I'm going to do first is write down everything that we know. We know that the change in internal energy as the system goes from A to B We worked this out in part I. It's 303 kilojoules. We also know the change in internal energy as the system goes through process B to C. That was 0 because it was isothermal. Now we are being asked, what is the change in internal energy as the system goes from C to A? But what we know is the change in internal energy of the entire process must be 0 because it is a closed cyclic process. And all it is it's simply the addition of all the internal energies at each point in the process. This is actually a really neat way to work out quickly what the change in internal energy is as the system goes from C to A. Because we know that this must be 0 and we know all the other values. Therefore, minus 303 kilojoules is the change in internal energy as the system goes from C to A. So that's great. We want to know, though, what this Q is. So now we've worked out the internal energy, we now need to work out what work is. Now, how are we going to work out what the work is? Well, we've been given a formula for work here. As the system goes from C to A, we can see that there is that the gas is actually compressing, going from 3 cubic meters to 1 cubic meter. And we also know what the pressure is at this point. This is just for small changes in volume, so what we can say is P times delta V. All we have to do here is work out what the area under the curve is. And we can see that it's just a rectangle. So let's go ahead and do that. The thing we need to remember, though, is that all of our values for pressure and volume need to be in SI units. So pressure needs to be in pascals and volume needs to be in cubic meters. So at A and C, the pressure is 1 atmosphere. To convert that to pascals, we multiply by 1.01 times 10 to the 5, and then we multiply that by our change in volume. So we're going from 3 cubic meters initially to 1 cubic meter finally. And then when we do that, we get 2.02 times 10 to the 3 joules, times 10 to the 5 joules, which is 202 kilojoules. Doesn't make sense that this value is positive. Yes, it does, because the way that we define work is when we do work on a gas, work is positive. And because the gas is actually compressing, the volume is decreasing, that means that we are doing work on the gas. So this should be a positive. So we can sub that straight in. And then when we calculate this, we get negative 505 kilojoules as our value for heat. In this question, if you correctly worked out what work is, you get a mark for that. If you correctly worked out what the change in internal energy is, being negative 303 kilojoules, you get a mark for that. And then if you get the correct answer with the correct sign, you get 2 marks for that. So part III is worth 4 marks.